All right, for those of you joining, welcome. So last week, remember we did an introduction to functions. Today we're going to learn more about those. So just some more snazzy topics you guys learn. So last week was an introduction. It was kind of boring, I'd say. Today's topics are definitely more interesting. So hopefully you guys find it that way. But let's move on. So hopefully you remember what a function is, right? Remember a function is like give examples like here g of x, right? So g is like the name of your function, and whatever's inside your brackets is your input, right? And then that would just produce an output. That was a so that's review for what a function is, right? So let's look at what composite functions are. So it's probably a new term for you guys. What's composite functions? It's basically in quotes you could call it a function inside a function. And this picture would give you a better idea of like what that looks like, right? So basically you're passing a function as input to another function. And basically how this works is that the output of the inner functions, you also have multiple functions inside a function. You don't, it's not necessarily just one function inside a function. You can have like three or even four or more. Yeah, it's crazy how much you can go. So the outputs of the inner functions is the input to the outer function. And this is the notation of what it looks like. So notation is you have, say your outer function is f, and then you have an inner function called g. This is what it looks like. So f, and then in brackets, then you have g of x. So g of x is inside the brackets of the f function, as you can see. Or you also have this notation. We don't use this one as often. This is called f at g of x. So this o right here, it just symbolizes like the word of or at. So f at g of x. This is the same thing as this one. But I think the left one, this one, f g of x, this one might be more easier to understand. And then this picture will show you, like, give you a better idea of what that looks like, right? So there's f of g of x, and then you have the f and then g of x inside the function. So it says here, like, g of x is the output of g, and this output of g of x is the input of f. So basically, whatever you get for g of x, then you substitute that into f of x. That's how a composite function works. Yeah, x is the input of g. Right? Any questions about this? Okay, if there are no questions, let me move on. Let's look at an example of composite functions in play. So, as an example, let's say we have f of x is equal to x squared, and we should also define a second function, g of x, because composite functions, we need more than one function to define. So we have g of x is equal to 2x plus 1. And say I want to find f at g of x. So this notation right here. Say I want to find that value. Basically what you do is you substitute in whatever g of x is, so 2x plus 1, and you put that as the input for the function f. So f of g of x is equal to f of 2x plus 1. So I substitute g of x into whatever's inside the f function, right? So f of 2x plus 1, and then you're substituting this into the x squared for f of x. So instead of x squared, now we have in brackets 2x plus 1, all that squared. Right? So that's how you substitute. That's how you substitute these inputs into the output. And then you can expand that, or you leave it like that. So if you expand it, you would get 4x squared plus 4x plus 1. And say I were to find f at g of 1. So I already know that f of g of x is equal to this expression right here. So 4x squared plus 4x plus 1. Say you want to find f at g of 1. You just substitute whatever is inside the g function as x. So remember, this was f of g of x. Now it's f of g of 1. So you're substituting 1 for x. So if you do that, you get 4 times 1 squared plus 4 times 1 plus 1, which is equal to 9. All right, so that's one way to find f of g of 1. A simpler way, so if you look at the right side, right here, so if you want to find f of g of 1, is instead of trying to find this expression, you can just substitute the 1 into g. substitute 1 into g of x and solve for that, and then finally get your wherever it is at f. Right. So you have f of g of 1 would be equal to f of, instead of 2x plus 1, we just substitute 1 into the x. So we have 2 times 1 plus 1. And that'll give you f at 3. And we're not done yet, right? We have to substitute 3 into the f function, which is x squared. So then you have f at 3 is equal to 3 squared. 3 squared is equal to 9. And you can see that we get the same answer as on the left side. So any of these techniques work. But if you want to find if you want to find the composite function at a specific value, so like not x, then I would just use this right side, like this technique on the right side. But if it just was f of g of x, then just, well, it's really similar technique right here. But yeah, I will use this technique on the left side right here. Right? Any questions? Okay. No, there are no questions. Let's move on. The next slide is a couple problems. Let's try this out. Here we go. Okay. So find the value for each of the following composite functions. So you have f of g of 2 is fx is equal to 3x, g of x is equal to x cubed, and then you have these ones as well. I'll give you guys 1 minute to solve these. And let me know when you guys finish too. I might have to give you guys some extra time. 1 minute's not enough. All right. I'll give you guys a couple more seconds. All right. Let's take up the first couple problems. Right. Can someone tell me what you got for 1? No, wait, I'm trying to find the, you see f of g of 2. I'm not trying to find the f of g of x, right? So I just want a number. Also, that expression is wrong, so try again. Yeah. Remember, use this technique on the right here. Right? That'll be easier than just doing all this. $24. Jerry got 24. I think that's correct. Yeah, 24. Here, let's take it up on the whiteboard. So you have what? You want f of g of 2. Right? Also, I should write f. Let me write the definitions again. So f of x was 3 of x. 3 times 3x, sorry. G of x. Oops. This was x cubed. Okay. Okay, so if you're using a technique on the right that I showed you guys earlier, you substitute 2 into g of x. So you just do 2 cubed right here. So this is f of 8. Right, and then you just substitute 8 into f right here, which is 3 of x. 3x, sorry. So this is just 3 times 8. And that's 24. So you get 24. All right. How about question 2? Anyone get an answer for question number 2? Not 1 over 15. Try again. Elaine got it? Yep, negative 1/5. So let's see how we got that. Perfect. Okay. So f of x was, so this was a fraction. This is 3 over x. It's called a reciprocal function. And g of x, that was, oh, just use p and q, whatever. I'll just use f and g, so why not? Sort of most often. Yeah, so yeah, usually people just use f and g as a function names. All right, so we're finding f at g of negative 3. So we just substitute negative 3 into g. So 6 times negative 3. Oh, it was not negative 3. It was negative 5. My bad. All right, it was negative 5. 6 times negative 5 plus 15. All right, what you get inside would be negative 15, right? So negative 30 plus 15. All right, and then you just substitute negative 15 into the f of x, so the fraction. All right, and then if you simplify it, you get negative a fifth. All right, that was fairly straightforward. Make some space for the third question. So someone tell me what they got for question 3. $200? I think it is 200. Here, let's see. Should be 200. So this is G and H. All right. Try and get a pencil. There we go. So G of x was square root of x. They have H of x is equal to, what is it? 4x to exponent 4. There you go. Okay, so we're trying to find G at H of 10. There you go. We could just use the techniques that we used over here, but let's try using that our technique where we just find G of H of x. So let me undo. Because you'll get a really large number, and trying to square root it might be a bit difficult for you at first. So maybe easier to like maybe try to simplify the actual expression first before we substitute in. So let's try that out. So we have G at, so hx equals 4x4. And we just take the square root of that because that's what G of x is. And if you simplify it, then you get 2x squared. And now it's easy to substitute. So we just do G of H of 10. This is 2 times 10 squared. So yes, it was 200. All right, nice job. Now, what was the final question? Let's go. All right, what did you guys get for question number 4? So yeah, instead of a number, now we just have a variable u. So we just want to find the expression, basically. So what did you guys get for question 4? This one's a bit tricky, so let's do it together. Okay, so a of x is x squared. We also have b of x. This is, what is it again? 2 to the exponent x. So this is an exponential function like we learned last week. Right, and we're just trying to find a at b of u. Right, so b of u is just 2 to the exponent u instead of 2 to the x, 2 to the exponent x. So 2 to the exponent u. All right, now we substitute this into x squared. So now we have 2 to the exponent u, and all that squared. And if you guys know your exponent rules, when you do this, you basically just multiply the exponents. So you just have 2 to the exponent 2u. That's your final answer. That's your simplified answer, that is. I guess you could leave it like this if you want to, but I think this is more simplified because there's no brackets, right? Okay, are there any questions about these problems before we move on? Yeah, Aiden, it was 2 to the exponent 2u, not u squared. Yeah, you're close. All right, if no questions, let's move on. The next topic, inverse functions. And it's pretty straightforward to what it is. It's just a function in reverse, but like, what is that in mathematical terms, right? This definition is not enough. So let's look in the mathematical term. Say we have some function f at x, and say we set y is equal to f at x. So y is the output of the function f at x, that is. And so if f at x is equal to y, then its inverse function, so we have this notation right here, this is the inverse function. So we have f at -1. So -1 is not an exponent, it's just like a symbol, it just symbolizes inverse function. So if you see a -1, that means it's an inverse function of f. So if we substituted y, so instead of x, we substitute y into the inverse function, you would get x, like your original input. So what does this look like? So it's like, say you have so you say you have a function x, and your original input is x, and your original output is y. Now if you instead make your input for the inverse function your output, so which is y, you substitute y into your inverse function instead of x, then what you get is your original input, which is x, what you get out of this, right? And I guess this is I don't know, this is like a picture of like what that kind of looks like. So you say you got an apple, that's your original input. If you pass it through f, you get a banana. Now if you pass a banana through your inverse function, you get back your apple. So you're back to the original input. So this is just like visualization of what this actually is. And if you were to look at this graphically, we're not going to focus on this too much, but just interesting to note, if you graph your function and your inverse function, the inverse function is actually reflected off the line of y is equal to x. So basically your original function's here, your inverse function's here, and this is like your axis of symmetry, y is equal to x. You can see that how like they're symmetrical to each other about that line. All right, are there any questions about this? Any questions? Yeah, hopefully this was a good analogy. Let's move on to the next slide. So how do we find an inverse function? That's what we're going to focus on. Right, find the inverse. So what do we do? Basically, we can sum up in these 3 steps right here. These 3 steps. So first, we set, so say we had a function of f at x, right? So that's what's given in the question. So you see in these problems, you're only given f at x. So first you set y is equal to f at x. Well, it could also be like g of x, but like just set y equal to the function, right? And basically you would get like, say for this example, say your f at x was equal to x minus 2, you just set y is equal to x minus 2 instead of f at x, right? For now, the second step, this is the most important step. you swap the x and y variables around. So what does that look like? So basically, if your y was on the left side and your x was on the right side, when you swap them, basically your x goes to the left side and then your y goes to the right side. So that's what swap means. Very straightforward. And say if you had like multiple instances of x and y, then you just replace all of them with the opposite variable. So say you had like two x's, you replace them with two y's. And say you had two y's, yeah, it's possible. If you have two y's, you just replace them all with x's. Yeah. And then your final step would just be to solve for y to get your inverse function. So for example, say our original function was x minus 2. First I set y equal to that. Your inverse would look like this. So you're swapping the x and the y. So you say, instead of y, you have x. So you have x is equal to, instead of x, now you have y. So x is equal to y minus 2. Now if you want to solve for that, let me get this. Okay. Yeah, this part's a bit annoying. Not sure why Google Slides has it right there. All right, so now if you try to solve for y, you get y is equal to x plus 2. So that's your inverse function for y is equal to x minus 2. All right, are there any questions about this? Any questions? Okay, if there are no questions, let's move on to some problems. Find the inverse for the following functions and determine if the inverse is a function or not. So I forgot to mention this, but sometimes the inverse is not necessarily a function. So remember that a function, like what definition is that for each input, it only produces one output. So if an input produces, say, two outputs, then it wouldn't be a function. So that's what determines if a function is, sorry, if an expression is a function or not. Right. So find the inverse for the following. Give you guys a couple of 1 minute. Then we'll take it up. Okay, let's take it up. So tell me what they got for question number 1. What do you guys get for number 1? Question 1. Does anyone have an answer for question 1? Y is equal to x minus 10 over 4. Yeah, Bob, that looks about right. Let's see. Let's use this space here. All right. So the function was, you have f at x. This is equal to 4x plus 10. All right. So first step was just to set y. You just basically replace f at x with y. So it's just y is equal to 4x plus 10. All right. So now you have this. Now what you do is swap the x and the y's around. So let's just say for the inverse, because now the equation will be the same. So That's why you have to like kind of say this line. I'll skip it next time, but just to let you guys know, like when you're in high school, when you're learning about the inverse, you're gonna have to write this line down. So you just basically like you're just saying like for the inverse, you swap the x and y around. So because now the equations are no longer the same, so we have to write this phrase down. So we have swapping x with y. So we have x is equal to 4y plus 10. And now you're just, solving for y. So you can move the 10 to the left side where the x is. So you get x minus 10 is equal to 4y. And now you just divide both sides by 4. So now you get y is equal to x minus 10 over 4. I guess if you want to write it in slope-intercept form, then you just get y is equal to a quarter x minus 5 halves. So 10 over 4, you simplify it to 5 over 2. Okay, so that's the first problem. Let's make space for the second one. Does anyone have an answer for question number 2? I mean, this one's a bit more tricky. Probably should put it at the end, but yeah. Well, let's try it together, actually. So we have f at x. Whoops. Yeah, they're all f at x. Okay, so f at x, negative 5x squared. Okay, so now we set y is equal to negative 5x squared. We're replacing f at x with y. That's what we're doing. Okay, and I'm supposed to write 40. Oh, not sure why I did that. Let's just pretend I wrote this line, but I'm just going to skip it, just save time. So now we're just swapping the x and the y around. So it doesn't matter if if x has an exponent with it, you're still swapping the variable. So now you have x is equal to negative 5y squared. So you're not swapping x squared with y, you just do x with y. So yeah, is equal to negative 5y squared. So that's how you do it. All right, now we're solving for y. First, you want to get rid of the coefficient. So if it's like a 5y squared, you want to get rid of the coefficient first. So we have negative a fifth x is equal to y squared. All right, and now you take the square root of both sides. But remember that when you take a square root, you have to do plus minus. Actually, I'm not sure if you guys learned this, but so we'll say you have like an equation such as like x squared is equal to 1. When you take the square root of both, you have to take a positive square root and the negative square root. So that's how you get two answers, right? So if you have a positive answer and a negative answer, that's how you get two answers for like a quadratic equation like this. So then this would just be x is equal to negative 1 and 1, right? For this equation right here. So if we look at this one, so this one's really similar. So we have basically just put negative 1/5 x inside the square root. And it's plus and minus as well. All right. So now you have y is equal to plus minus the square root of negative 1/5 x, right? And there's a second part of the question that said if it's a function or not, and it's actually not. The reason why? Well, let's actually graph this on Desmos. Graph it on Desmos. So we have square root of negative 1/5 x. Hopefully this loads. Okay. So we have, I'm going to separate this into two parts. So remember, we have a positive square root and a negative square root. Let's write both those down. There, and then y is equal to. This is let's make a top one in positive square root. So red line's positive square root. Let's make this, I think it's blue line or something. Here. Right, it's a blue line. All right. So this is a positive square root right here. Negative 1/5 x. And this is a negative square root. So we have negative square root of negative 1/5 x. And you see that this is not a function because say I took one of these numbers, so -8, you can see that it produces two outputs. So you have a positive version of that. So like positive 1.26, 1. Yeah, you have positive 1.26, but you also have a negative 1.26 around here. So you see that these values produce two different inputs. So that means that this is not a function. And remember that you can also use a vertical line test to test if it's a function or not. So if the line, so let's draw a vertical line anywhere, and if it passes through two or more points, then the graph is not a function. All right. So that means that our final answer, so the inverse, is not a function. Well, that's that. So let's go back to the slideshow. Did you guys get an answer for question number 3? And you could say it's like a rotated parabola. It has the same shape actually, but it's rotated. So it's no longer a parabola. It's just, you just call it a root function. It's called a root function. Yeah. Even though it has the same shape, but it's rotated. So it's no longer a parabola. Did any of you get an answer for question number 3? I think this one might be a bit easier than number 2. Okay, let's take it up. So we have f of x is equal to square root of x minus 10. Oh, that ended ugly. Okay. First thing you always do is set y equal to that. Okay, right in zeros. Okay, there we go. Now we just swap the x and the y around. So remember, it doesn't matter like what's around the x. We just change the variables. So we just x is equal to square root of y. Basically switch positions. So x is equal to square root of y minus 10. Right? I'm going to just move the 10 to the side where the x is. So we get x plus 10 is equal to square root of y. Right? And now just to get y by itself, you just square both sides. We don't care about the plus or minus anymore because squaring it just makes it positive anyways. So we just have y is equal to x plus 10 squared. Right? So that's your function. So y is equal to x plus 10 squared. You could expand this if you want to, but usually leaving the brackets like this is, I don't know, usually a more simplified version. And this is a function actually, because it's a parabola, as you can see, x plus 10 squared. Right? Let's go back to the last question. So, okay, number 4. F of x is equal to 1 over x. Someone get an answer for that. Oh, your internet cut out, Yifang? When did it cut out? Do you remember? Around this third slide, like third question, like this one. I think that's what you mean. Basically, hopefully you were there when you took up like the first problem or whatever. But yeah, I'll hope we were just taking up those problems. Nothing too important. So, well, Aiden, you said was this F 0.1? Not sure what you mean. Okay, you know what? Let's take it up. So fx is equal to 1 over x. Let's take that up. Whoops, did I mean to draw that? Here. So fx is equal to 1 over x. Y is equal to 1 over x. Right? Now we just switch the x and the y around. So we get x is equal to 1 over y. So now we want y by itself. First, let's get rid of it from the numerator first. Sorry, denominator. So we just multiply both sides by y. So now we just have x times y is equal to 1. Now we get y by itself, we just divide both sides by x. So y is equal to 1 over x. That's your inverse. And it's also a function because, if you do any value for x, you just get one value for y. So it works out. And also notice this is really cool. The inverse for the reciprocal function is itself. So you see that the inverse stayed the same for 1 over x, which is really cool. Right? Any questions about these problems before we move on? Any questions? Right, hopefully not. Let's move on to the next slide. Let's look at even and odd functions. What are these? All right, so what's an even function first? Even function is a function where, say you have some function f at x. So if you substitute f at negative x, and this is equal to the original function, so f of negative x is equal to f at x, then you get an even function. All right, and what does this mean graphically? So remember last week we learned about like transformations, reflections more specifically. Remember that if you have a negative inside the input, that means you have a reflection off the y-axis. So like from here all the way to there or something like that. So what this means graphically is that, so f at x, the original function, is equal to its reflection off the y-axis. All right, so here you have an example of, so this is the x squared function, fx is equal to x squared. And you see that it's like symmetrical off the y-axis. So even if you try to reflect it, it'll stay the same. So that's why it's an even function. Right? Now let's look at what an odd function is. An odd function is a function where you have f at negative x. Instead of equal to the original function, this is equal to negative the original function. So negative f at x instead of f at x. Right? And what does this mean graphically? This means that, remember that if you have a negative in front of the function, so remember last week reflections, if you have a negative in front of the function, this is a reflection of the x-axis. So you're going from top to bottom or bottom to top, right? So this means that a reflection of the x-axis, so for negative f at x, is equal to a reflection of the y-axis, so f of negative x. An example of that would be, so you see in this picture right here, this is the x cubed function right here. So you see that if you reflect it on the x-axis, so basically this part moves over here, this part goes over here, so it looks like that. So this dotted line right here. And if you reflect it off the y-axis, you get the same thing. So this part would go over here, and then this part right here would go over here. And still, it's the same graph, as you can see. And you can also say f of x is equal to negative f at negative x. But I think this one's more easier to understand right here. So you have a reflection of the x-axis is equal to a reflection of the y-axis. Right? And also note this. Some functions can be neither even nor odd. Right? So this is only for some specific functions like x squared, x cubed. Some of the functions don't have to be either even nor odd. Just to let you guys know. All right? Are there any questions about this? Any questions? All right, let's try the following problems. So determine if each of the following is even, odd, or neither, right? I'll give you guys, a minute to figure these out. Shouldn't take too long, hopefully. Oh yeah, and also a function can be both even or odd, right? It has to be one of them. If it is, that is. Right? Okay, let's take it up. What did you guys get for question number 1? Is that even or odd or none of them? What did you guys get for question 1? Jerry says even. Jerry is correct. You are correct. Let's see why. Let's go to the whiteboard. Okay, let's take out a drawing tool. So let's find f of x. Well, obviously, that's the function itself. So let's just write that down. This is x to the exponent of 4. Now let's calculate both f of negative x and also negative f of x. So let's do that. So first f of negative x. So this would just be negative x to the exponent of 4. And so to simplify this, you can see that, so since it's a negative inside the exponent of 4, and 4 is even, right? So we're multiplying this negative by itself 4 times. And basically it would just cancel it out, right? If it's an even number. So this means that you would be left with x to the exponent of 4. Right? Hopefully that was straightforward. And negative f of x. This one is fairly simple. You just put the negative in front of the x to the exponent of 4. So yeah, I don't think f of x can be ever equal to negative f of x. I don't think that's ever possible. But yeah, you can see that f of x is equal to f of negative x, right? They're both equal to x to the exponent of 4. So that means this function is even. So it's an even function. All right, let's go to question number 2. What did you guys get for question number 2 right here? Even, odd, or neither? Let's answer for question number 2. Let's try it together. We have f of x is equal to negative 5x cubed. All right. Now let's find what f of negative x is. So this is negative 5 times negative x, all that cubed. So you have a negative x, and then you take that cube and cube that. So it means you're multiplying a negative by itself 3 times. And so then you're just left with one negative because 3 is an odd number. Then you still have a negative here. So you get negative 5. Just do the extra step. So this is negative 5 times negative x cubed. So you see that the cube now is from the x, and negative is also from that whole thing. So when we simplify it, we just get rid of these two negatives. So this is just 5x cubed. Right? And finally, negative f of x. So this is just negative, and then we'll just put the negative 5x cubed inside brackets. You can see that these two negatives cancel out to get you 5x cubed. So you can see that f of x is not equal to any of these, but you can see that f of negative x is equal to negative f of x. So that means that this function is odd. So this is an odd function. All right, let's go back to the slideshow. Can someone tell me what you guys got for question number 3? What you guys get for number 3? No, it's not odd, Bob. Yep, it's neither. And got it. So let's see why. So this is a linear function. F of x is equal to x minus 10. So let's calculate what f of negative x is. Simple, you just substitute negative x for x, so just negative x minus 10. Now we have negative f of x. So instead of just a negative for the x, now you take negative for this entire thing. So we have negative and brackets x minus 10. So this is just negative x plus 10 if you expand it. Right, now you see that none of these are equal to each other. Right, so f of x is not equal to f of negative x. F of negative x is not equal to negative f of x. So that means that this is neither even nor odd. So just put neither. That's question 3. Can someone tell me what they got for question number 4? Right here. It's question number 4. What did you guys get for question number 4? No answer. Here, let's try it. So f of x is equal to 1 over x. It's the reciprocal function again. All right, so f of x is equal to 1 over x. Now you want f of negative x. So now we just have negative x inside the denominator. We can just move it in front of the function, in front of the fraction. Then we also have negative f of x. This is very straightforward. You just put a negative in front of the entire fraction. Now you can see that f of negative x is equal to negative f of x, not equal to f of x. So this function is odd. All right. So that's that. Are there any questions about these problems? Any questions? Okay, now let's move on to something spicy. Let's look at recursion. It's very cool. So what does this term mean? In a gist, it just means that you're defining a function using itself. And I'll show you guys an example of what that looks like. So this is usually used in like sequences of numbers, right? And so definition for a recursive function, it requires one or a few base cases. So this means like defined cases where you have like, I'll show you guys an example of that later. So you have one or a few base cases before you define your recursive formula. So your recursive formula is where you define a function with itself. And a famous example of this is the Fibonacci sequence, right? So if you were to write like how it's defined in function notation, you get that the first term is equal to 0. Some people say it's equal to 1. I don't know, you can set this equal to 1 or 0, it doesn't matter. So say f of 1 is equal to 0. Now you have f of 2 is equal to 1. So these are your base cases. That's what that means. So you have defined, so for a defined input, you have a defined output. That's what base case is. So that's that. And then you have your recursive formula. So this is your recursive formula. So you have f at n is equal to f at n minus 1 plus f at n minus 2. So what does that mean? So you see that it's defined using itself because you have f at n right here, and you also have f functions on the right side. So that's why it's a recursive formula. Like, what does this mean? Like, like how does it relate to Fibonacci sequence, right? So you have f at so say n was a term number, right? And remember that in Fibonacci sequence, a term is equal to the sum of its two previous terms. So you have f at n minus 1, so that's the most recent term. And then you have plus f at n minus 2, so that's two terms before the current term. So if we try to find, say, f at 3, so say f at 3, this would be equal to f at 3 minus 1, which is f of 2, and plus you have f at 3 minus 2, which is f of 1. And you see that f of 1, f of 2 are defined. So this means you get 0 plus 1, which would give you 1. So f of 3 would equal to 1. And then you just continue that with the other terms, right? So you have f4, that would be f3 plus f of 2, that would give you 2. And you have f of 5, that would give you 3. And then you have 5 and 8 and so on and so on. So that works. Yeah. And say if you map out all of your calculations, so it will look like a tree if you try doing the diagram. So if you see this example right here, this tree right here. So you have f of 4. This would be equal to f of 3 plus f of 2. And for each of those, you continue to branch out. So you have f3, you branch out to f2, f1. f of 2, you branch out to, I know it's not here, but you have f1 and f0. Yeah, f2 right here, you branch out to f1 and f0. And you can see that it looks like a tree of like branches. That's why it's called a tree. Right? And this is like used very often in computer science. Basically, you're just calling a function on itself. So if you can see the example on this left side, basically, if you've done computer science before, if you know what functions are, yeah, there's functions in computer science. So it looks like this. So you have something called void recurse, and then this recurse function is So this recurse function is used inside the actual definition, as you can see. So this is called a recursive call, as you can see here. And then basically when you call recurse or the function call, it'll just call recurse on itself. So yeah, very complex. It's a bit complicated, but you guys learn more about it later in high school. But yeah, and what can we do with recursion actually in art, say? So we use in art. We can use it to make these cool patterns called fractals, right? So let's take a look at this animation right here. This one on the right here. This is called the Mandelbrot set. So basically, it's like this really cool pattern of like circles. So you see, actually, maybe I'll wait for the actual pattern to appear. So it kind of looks like I don't know, like a circle with a bunch of circles like mixed together. But should probably not make this an animation because I have to wait for it. But here, let's focus on this. Oh, right there, Mandelbrot set. So you can see that was the initial pattern, and basically you can see some of the same patterns repeated inside as you zoom in out. So see, the Mandelbrot set is repeated. It's like a repetition, as you can see. So you can see like individual Mandelbrot sets inside of this entire pattern, which is very neat. And you'll learn how to code this in if you take grade 12 computer science. So make sure to take that course when you go into high school. But yeah, here's another example of a fractal right here on the right side. You have, this is called Sierpinski triangle. I know a lot of you might have heard of like Legend of Zelda, and you've seen like a logo that looks like this. And this is the logo is a Sierpinski triangle. So you can see that like first you divide this into like 4 triangles, then you divide it into even more triangles. So for each of the black triangles, you make more Sierpinski triangles. And then you just keep doing that, and it repeats infinitely. So as you can see right here. Yeah, that's very cool. It's really cool use of recursion, right? Any questions about this? We're not going to do any problems about this. This is a very complex topic, but like, just good to know. Yeah, it's called Triforce. Yeah, Aiden, it's called Triforce. You don't play Legend of Zelda? Yeah, I call it Triforce, but we'll call it Sierpinski triangle in, I don't know, mathematical terms or whatever. If there are no questions, let's do some final problems. Let's try this one out, okay? Find f of g of x and g of f of x if f of x is equal to square root of x and g of x is equal to x squared. All right, I'll give you guys a minute to figure that out. Jerry got the answer. It's x for both of them. Right? Let's see why. So we have, let's look. So we have f at x. That was a square root 1 if I'm, yeah, square root of x. And now we have g of x is equal to x squared. All right. So, okay, let's pan down. Okay, so we have f of g of x this is equal to, so we have f at x squared. So we're just substituting x squared into g of x. All right, and then you just substitute this x squared into whatever f at x is, which is square root of x. So we're taking square root of x squared. So if you take the square, sorry, if you take the square root of a square, you're basically getting rid of that, right? That square, the exponent 2. So we're just left with x. All right, so that's f of g of x. Let's look at g of f of x. And yeah, it's the same thing. So you have g at square root of x. G at square root of x. All right, and then you substitute square root of x into x squared. So we have square root of x. And then you square that. And if you square a square root, you just basically get rid of the square root. So you're also left with x. So you can see that both of these are equal to x. Very neat. All right. Oh yeah. I guess it's for only for these specific functions. So square root of x and x squared, where f of g of x and g of f of x are equal to each other. It's not always that. It's not always this case for other functions. Say I had like, I don't know. Say I have 3x squared right here. That it'll make it completely different. Right. So this is just like a specific case where these two are equal to each other. They're not always equal to each other. Any questions about this? Before I move on.